It's time to use cross-validation with random forest. Here we go. I might just take out this linear regression model. We've already looked at this. And let's get cross-validation in here. So it's from sklearn.model selection. Okay, I think. Import cross-val score. Okay, that's the one that we want. Cross-val score. Okay, we're going to get the scores using cross-validation. Now, we need to have a model, okay, and an X and a Y. So for the model, what gave us the strongest so far? I think it was, I feel like, was it something like this? I'm just going to tweak this a little bit. Let me just run that again. No, it didn't. Okay, it was something like that. Okay, we could start afresh, really. Let's just put in a model. Let's do a default one. Random forest regressor. Let's start with the defaults. And what we're going to do now is use that inside of cross-val score. So cross-val score, you got to put the model in there, okay? And then you put your X and your Y. Now, okay, based on where we are in the curriculum, which is, we're in the process of learning sort of why people do things with machine learning, we're just going to leave this as X and Y, because instead of us doing the train test split, we're going to actually allow cross-validation to do that split for us. The reason why I'm making a point of this is because, what you'll see later is that it can be good to actually hide a test set, okay, like X test and Y test. And then you spend, who knows how long, could be days, could be weeks, could be months, could be more, finalizing your machine learning model. And at the very end, you actually test it on the hidden test set. And so during this process, you would validate on your training set. But for us, for now, okay, we're just going to do it on regular X and Y. And let's see what happens here. Okay. I'll show you guys how to add in the different parameters. Now, it is going to take a little longer here because instead of doing one random forest, right, it does 1, 2, 3, 4, 5, right, and it gets 5 scores. And here you can see the variation that there are some, look at the second one. There are definitely some challenges within the test data, right? Like when it's testing on this one segment, it performs much poorly than the others, okay? So let's go ahead and put in, I think we want to do more like what we were doing. Let's see what we can do working in tandem with cross-val score and the random forest. Maybe this was at 8. These could have been at 7. I'm not really sure. Maybe this one was 7. And in estimators was higher. Now, I don't want to make it too much higher because it takes longer, right? Doubling the number of trees is going to take you close to doubling the number of time. But we got a little better scores, I think, doing something like that. So we'll give it another whirl here. Now, these are producing scores of your data. And it can be instructive. You can see on average, this is a little higher, like this fold looks good. The second fold is still problematic, which is very interesting, I think. So, it can be nice to look at both the scores and the mean scores. Okay, so I will sometimes do something like this. You set your scores equal to cross-val score, and then you can even print out both. You can print out your scores. You also print out your mean score, right? Because really that's what you want to know. It's nice to look at it like this, but how are these balancing out? What's the mean score that we're getting? Meaning we add all these up and divide by the number. Array means this is a NumPy array, so you can definitely do dot mean to get the mean score. So, we already have this. Okay, let's just run it here. Oh no, because I didn't define scores. Okay, let's just run it again. So we're taking the time to rebuild the same model. I think with cross-validation, it does the splits in the same way. And what we can look at, so here we got 48. It's, this one is really slowing it down. So how do we fix the CV? Okay, it's the cross-validation. So you set CV to the number. So this is 4,000, so we're getting big test sets. So maybe we want to do more like 10, like split it more into 10 models. So if we split into 10, you're still going to have like 400 basically for each test set. Now it can take a little longer, okay, but let's see what happens if we change it to 10. And as it's giving us a score, I want to highlight something else that's critical here for regression. So this is giving us the R2 score. And the R2 score basically tells us on average, how much of the data is explained by the model. Well, what does this even mean? You can see we did not get a better mean, okay? Ooh, but we're finding some really rough patches in here. So, hey, it is what it is. So I don't like this scoring metric and I don't actually use it. And believe it or not, it is not the norm with regression. So within cross-validation and with all of machine learning, you can actually choose the scoring metric, but it has to make sense with your data, okay? So I'm going to leave this up, okay? I'm going to put this back down here. To speed it up a little bit, I'm going to leave CV at 5, and I'm even going to cut down the in estimators to 100. Sometimes I'll tweak like one thing or two, like what if we lower this just a little bit? Okay, so what about the scoring? Okay, I believe that the parameter is called scoring. Yeah, you see it up there, scoring. And there are different like metrics. So what we're doing is the R2. Now, I think what they have is the mean squared error. Okay, we're going to try this and see if it works. And then I'm going to talk about how you deal with the mean squared error in the right way. So, what's nice, it wasn't mean squared error, but it tells us the correct ones, and I think it's negative mean squared error. Okay, yeah, and that in itself can be confusing. It's nice when they actually tell you. You can always look it up. So again, we'll talk about how to deal with this properly, but let's just see how the scores are put out here. Okay, so we get these scores, and like, what do these scores even mean, right? They're not like, they're not meaningful, but they're very close to being meaningful. All you have to do is take the square root. Okay, when you take the square root, okay, so this is what we're going to do. Let me just make a note here. So taking the square root gives the RMSE. That's the root mean squared error. And what that tells you is how far away your points are from what they are trying to predict. It is the most meaningful regression interpretation that you can have. There's no ambiguity to it. So what you need to do from the squared error is you've got to make it negative, okay? And then simply take the square root. Okay, and I'll put it out there. So for RMSE, we take negative scores, okay, and then to the 1/2 power. Okay, so you have to do this little extra line to get it, but then we can print in the RMSE and the means. Now when we do this, now when we've changed the metric, we don't actually know like if we make a change, if it'll improve or not, because we're looking at it in a weird way. And before I run the code, you may wonder, why the heck is it negative? It's because of how sklearn stores their scoring metrics. And so it's kind of like with percentages, higher is better, but root mean squared error, lower is better. You want the smallest error. So the smallest error here would be this -2. Well, that's the highest one. That's why it uses negative. So it's following their sort of own, their own way of organizing scoring metrics in general. Okay, so you don't want higher is better with the root mean squared error. We did want that with R2. We want lower is better, and we want to make it the positive square root. So now when we run it, we're going to get some numbers back, okay? And what these numbers, here, there they are. What these numbers tell us is something much more meaningful and much better than what we were getting. So what does this mean, this 2.13? I will add a text cell and tell you, okay? So generally speaking, the RMSE is the error of what you are trying to predict on average, okay? In this case, we can expect the number of rings, that's what we're trying to predict, to be off, okay, the error, by about 2.13. That is the whole point, okay? When you get the RMSE, okay, you're trying to get as low as possible, all right? And that's what it means. So if you look at your data now, okay, so we're trying to predict, well, it's just Y. Like how does Y line up? Well, excuse me. Here we see, okay, so we've got ranges of rings from 1 ring to 29. The average is about 10. The standard deviation is 3.22, meaning, you know, when you're looking at the spread of the data, you expect them to be about 3.22 off from the mean. And so in effect, that's a nice one to compare it to, because you can see that you're actually learning something. You're actually getting something that is closer. So, it's not that like, when you're comparing scores, you can really compare R2 with the RMSE. It's that in most of the world, okay, most people who do machine learning on regression will often use the mean squared error because it's faster when you're doing the computations, but then take the square root at the end because it leads to the direct interpretation.